Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So let's start with chapter number 2, part number 2. So the title for this part is the cascade blade profile. So in this slide we will learn how to characterize the specific shape of a blade. Okay, now is about the cascade nomenclature and also blade profile. So in order to describe and also characterize the shape of a blade, we need to know the parameter that involved for the blade profile. So these figures shows the rotor of the turbine and also the rotor of the compressor. So previously we already discussed the different in terms of shape of blade for the compressor and also for the turbine. For the compressor will have a flat shape blade. However, for the turbine will have curved shape of blade. So in order to describe the specific shape of the blade, we need to know the blade profile, the parameter that involve to describe a specific shape of a blade profile. So the figure shows the schematic diagram of a single blade in two-dimensional view. So we call this shape as a blade profile. So the red color dashed dotted line represent a camber line. So this camber line actually shows the basic shape of the blade profile. And we have at the front of the blade, we have the leading edge point, which is normally used as the point where the inlet of the fluid flow throughout the cascade blade. The second point is the trailing edge point, where this point also normally we refer as the outlet point for the fluid flow come out from the cascade blade. So if we connect these 2 points and make a straight line, so this line we will call the chord line. And if we draw the vertical line at the leading edge point perpendicular to the chord line, so the x direction distance, x we refer as the horizontal distance. However, the distance in y direction we call the vertical distance. So the distance between the leading edge point and also trailing edge point we call blade chord length, that described by the parameter of L. Parameter of T represent the profile thickness. T actually is a function of x, where this parameter actually depend on the distance of x, which means at certain distance of x, so we will have different value of profile thickness, different value of T. So we can measure the value of T by measuring the vertical distance from the lower surface of the blade profile up to upper surface of the blade profile at certain x distance. B actually is referred to the maximum camber and is considered as a y function because direction for B is in y direction. This value actually the highest thickness of the camber line, and measured from the chord line by using the perpendicular line to the chord line until the point where the thickness is at the highest condition. And A refer to the distance start from the leading edge point to the point where we measure the maximum camber, which is referred to point B. So that's a few parameter involved with blade profile. Now we consider about the cascade nomenclature. In the figure we have 2 identical blade profile. In the figure shows the camber line of the blade, also the leading point and the trailing edge point of the blade. So if you connect both points, so we will get the chord line as we mentioned in the blade profile discussion. So the distance between trailing edge point and also leading edge point will give you the value of blade chord length. So let's draw the reference point based on the trailing edge point and also leading edge point. So if we draw vertical lines at the leading edge point and we measure distance between leading edge point for different identical cascade blade. So we will get the parameter of S, which is represent the spacing distance of the cascade blade. So the angle between chord line and also the vertical line at the leading edge point represent the stagger angle that represented by the zeta symbol. So if we draw a tangent line to the camber line at leading edge point, we will get the leading edge line, and the angle between this line to the vertical line at the leading edge will give you the angle of alpha 1 prime, which is equal to N3 blade angle. Then if we draw the tangent line to the camber line at the trailing edge point, so we will get another line that we call trailing edge line. And if we draw vertical line at the trailing edge point, the angle between trailing edge line and also this vertical line actually is exit blade angle that represented by alpha 2 prime. So next, the angle of theta, where the angle of theta is actually the angle between trailing edge line and also leading edge line. And the theta angle represent the camber angle, where we can calculate the camber angle by using this formula, where the theta equal to alpha 1 prime minus alpha 2 prime. Alpha 1 prime is the N3 blade angle, alpha 2 prime is the exit blade angle. Okay, so now we need to consider the fluid velocity vector C1, where C1 is the inlet flow velocity vector and C2 is the outlet flow velocity vector. So the angle between C1 and also the vertical line at a leading edge point, the angle is referred to the inlet flow velocity angle that represented by alpha 1. However, at the outlet, the angle between outlet flow velocity vector and also the vertical line at the trailing edge point will give you the value of alpha 2, which is equal to the outlet flow velocity angle. So now at this point, you need to know what the difference between alpha 1 prime, alpha 2 prime, and also alpha 1 and alpha 2. So N3 blade angle or exit blade angle normally fixed, will have the fixed value depend on the blade profile shape. However, the flow velocity angle consists of inlet flow velocity angle and also outlet flow velocity angle, normally change depend on the condition of the fluid flow at the inlet and also at the outlet. Okay, next, I actually is an incident angle, where we can calculate by using the formula of alpha 1, which is inlet flow velocity angle, minus alpha 1 prime, which is N3 blade angle. But if you refer to the figures of the cascade blade arrangement, I actually is the angle between inlet flow velocity vector and also the leading edge line. The last one, we have delta, which is represent deviation angle. So the angle between outlet flow velocity vector and also the trailing edge line. So in terms of equation, deviation angle actually equal to alpha 2 outlet flow velocity angle minus alpha 2 prime exit blade angle. So that's the parameter involved with blade profile and also the nomenclature for the cascade blade arrangement that we will use later on in the analysis of the turbo machinery. Okay, now in this slide I will explain a little bit about the additional info related to the blade profile. So previously we already learned about the parameter that involved with blade profile as shown in these figures, and one of the most important parameter is the blade thickness or the profile thickness, which is referred to the T. Okay, so this T actually refer as the profile thickness, where this value of thickness depend on the direction of X, the distance of X, where at specific distance, so we will have different value of blade thickness. And we consider this parameter as the local blade profile thickness, which means at different X distance, so we will have different value of blade thickness T value. However, we have another main important parameter in blade design, which is the maximum blade profile thickness, which is referred as T maximum, where most of the I call parameter that we'll use to design or to develop the blade profile also will refer to this value, T maximum. Okay, and T maximum we consider as one of the main parameter in blade design, and normally the location of the maximum blade thickness is approximately around 30% to 50% of chord length from the leading edge. Okay, so normally this value depend on the what I call the blade design requirement, and also depend on the application of the machine that use that kind of blade. Okay, another info that important to you to understand is about the blade profile in terms of principle, where a cascade blade profile can be created or formed as a curved camber line upon which a profile thickness distribution is symmetrically superimposed, which means, for example, if we draw what I call the chord line, and then draw the what I call the trailing edge line plus the leading edge line, so we can draw, we can estimate the shape of the red line represent the camber line. Okay, so based on this principle, we know that the distance I call from the center line, from the camber line to the upper surface of the blade will be equal to the distance between the camber line and also the lower surface of the blade. Okay, of the blade. So in that case, we can draw at specific distance, x distance, on the camber line we can draw a circle that represent what I call the same distance or symmetrically superimposed in terms of the distance between what I call the camber line to the upper surface, and also camber line to the lower surface of the blade profile. Okay, so we need to have this information at specific distance. We need to have the specific thickness value. Okay, so from this concept, easily we can draw specific shape of the blade profile by referring to the what I call the tangent line at each circle that we make. Okay, so based on the circle, we can see that if you make a line that that perpendicular to the camber line, so the distance, upper line in terms of distance, and also lower line in terms of distance will be the same, will be equal. Okay, so that's the meaning of this principle, where the cascade blade profile can be created or formed as a curved camber line upon which a profile thickness distribution is symmetrically superimposed. So later on in our class, we will discuss how to create this blade profile by using this method, where I want you to have two important skills related to the blade profile. Okay, later on we will discuss. Okay, now try to look at this example 2.1. So you need to answer the question. So the figures shows in the example is a profile of a reaction turbine blade by using a geometric approach, ruler, protractor, and others. Determine A, the maximum blade thickness, B, the blade chord length, C, the maximum camber, D, the distance from the leading edge. So for your information, there are two approaches that can be used to solve the problem. First, by using a geometric approach. So you need to use a physical items such as rulers, protractor, and so on to measure the parameter of the blade profile. The second approach, by using a trigonometry approach, which means you can use any trigonometry equation formula to determine the parameter of the blade profile. However, for this example, you need to use a geometry approach. Okay, now let's try to solve this example 2.1. So now we have the actual features of the blade profile that mentioned in example 2.1. So first, the question asks you to determine the maximum blade thickness. So first, what you need to do, you need to draw the chord line. So in order to draw the chord line, you need to connect the leading edge point and also the trailing edge point. So you get a line that we call the chord line. Okay, next step, take a ruler and make sure that the ruler is perpendicular to the chord line as shown in the slide. Okay, then move the ruler along the chord line and then identify the maximum distance of T. So that's how we obtain the value of maximum blade thickness. So measure the line. So the line will give you the value of maximum blade thickness or maximum profile thickness, more or less equal to 2 cm. Question B, blade chord length. So you need to measure from leading edge point to a trailing edge point, or you can make perpendicular line at the leading edge point and also perpendicular line at the trailing edge point and measure the distance. So the distance will give you the blade chord length, which is equal to L. L equal to 17.33 cm. Okay, so in order to measure, you need to use a ruler. Okay, C, maximum camber. For maximum camber, you need to move the second ruler upward and downward until you get the highest point of the camber line. Let's say at the second point, and then draw the perpendicular line to the chord line and intersect with the point. So you will get the value of B, which is referred as the maximum camber, and the value will be 2.65 cm. Okay, the last one, the distance from the leading edge. So you need to measure from the leading edge point to the point where we measure the value of blade thickness. Okay, by using a ruler, measure the distance of A, so you will get 8.51 cm. Okay, now we already learned about the cascade nomenclature and also blade profile, where we already learned how to characterize and also how to know the specific shape of a blade. Okay, so now how we want to know the specific blade names. So normally, in order to name the specific shape of a blade, we will use Nakka Method or Nakka Code. Okay, this figure shows the parameter that we have learned during discussion on the blade profile. So this parameter also will use in Nakka Method or Nakka Code. Okay, so these are the example of the special shape of a blade with different code of Nakka Code. So the first figures shows the blade shape of Nakka 2412. So we also have Nakka 4412, Nakka 8412, and also Nakka 8610, which means different Nakka code will give you different shape of blade profile. Okay, so there is another example of the Nakka code, but for this case, for Nakka TN3802, so we have 5 different blade shape but still under the same Nakka code. So the difference of blade shape actually due to the change of camber angle, start from 65 degree to 120 degree, and also the change of the value in terms of profile thickness to chord length ratio from 10% to 25%. For T/L ratio, the parameter T actually refer to the value of T maximum,
and the parameter L refer to the chord length.
So in order to determine I call the camber angle and also T over L ratio, so we can use the method that we have learned, the geometry approach. Just draw the estimate camber line and draw the leading edge line, draw the trailing edge line. So the angle between these two lines will give you the camber angle theta. Find out the highest thickness of the blade and measure it. You will get the profile thickness T. The distance between the leading edge point and also the trailing edge point will give you the value of blade chord length. So you can determine the value, or you can change the value of camber angle and also T over L ratio. Okay, from previous slide, I already mentioned about the Nakka approach or Nakka code in order to name the specific blade profile. So in this chapter, we will learn two types of Nakka code. So we have first Nakka 4 digits. The second one is Nakka 5 digits. So the figure shows the important parameters of blade profile that use in Nakka 4 digits codes. So we have the
Maximum profile thickness, T max.
we have maximum camber B, we have the chord length distance L, and also we have the distance from the leading edge, and which is represented by parameter of A. A represent the position of the maximum camber. Okay, for Nakka 4 digits, these are the format for Nakka 4 digits. So we have Nakka terms. First term is Nakka, stand for National Advisory Committee for Aeronautic. The second term is for M code, where this M code represent the maximum camber value, where we can calculate the value of M code by using the formula of P equal to 0.01 m multiplied by L. The third term is for P codes, where this P code represent the position of the maximum camber A, where we can determine the P code number by using this formula, where A equal to 0.1 P multiplied by chord length. Okay, the last term is XX code. This value represent
The maximum blade thickness,
and we can calculate the value of XX code, the number of XX code, by using this formula, where
T max, the maximum blade thickness,
equal to 0.01 XX multiplied by chord length. Let's see to the example of 4 digits code. For example, Nakka 2410. So from the code, we can determine the value of maximum camber B. So B equal to 0.01 multiplied by M code, which is equal to 2, multiplied by chord length L, which is equal to 0.02 L. So B, although we doesn't know the exact value of chord length, so we will get the generalized value of B, where B now equal to 2% of chord length. And
the second term,
which is represent the P code. The value for P code in this example is equal to 4. So from this value, we can determine the value of position of the maximum camber A, where A equal to 0.1 multiplied by the value of P code 4 multiplied by chord length. So we will get A equal to 0.4 L, which is represent 40% from the chord length value. And the last term, the code for XX. So for example, XX equal to 110. So in order to determine the
maximum profile thickness, so T max equal to
0.01 multiplied by XX, which is now equal to 1.10 multiplied by chord length, so equal to 0.1 L. So now
T max
equal to 10% of chord length distance. So let's say if the chord length distance equal to 100, let's say 100 centimeter, so we will get the value of B at 2 centimeter, the value of T max at 10 centimeter, and also the value of A at 40 centimeter. That's how we interpret the Nakka 4-digit codes for specific blade. Okay, next is about the Nakka 5-digit codes. So the figure shows the blade profile with certain parameters that involved with Nakka 5-digit codes. First, we have the blade profile thickness T. Second, the distance from the leading edge point A, and also the chord length distance L. And this is the general I call Nakka 5-digit codes. So we have first term Nakka, stand for National Advisory Committee for Aeronautics. Second term L code. This code represent the lift coefficient value, and the value for the lift coefficient CL can be determined by using this formula. CL equal to 0.15 multiplied by the L code value. The third terms is P code, where this P code value represent the position of the maximum camber A, and maximum camber, the position of the maximum camber A can determine by this formula, where A equal to 0.05 times P codes times chord length distance. And the fourth terms in this code is Q code, which is represent the type of camber line. So there are two type of camber line. So the value of Q will be 0 if the blade profile use the normal camber line, as shown by the first figure of camber line. The value of Q will be equal to 1 if the blade profile use the reflect camber line, as shown by the second figure of camber line. Okay, the last term for the code is XX code, where this XX code represent the
maximum blade thickness T max,
where we can obtain the value of
T max
by using this formula.
T max
Equal to 0.01 times XX code value times the chord length distance. Okay, let's see one example for this Nakka 5 digits. So let's say we have Nakka 23012. So from this blade profile code, we can determine the parameter, for example, the value of lift coefficient, where lift coefficient from this code equal to 0.15 times the value of L code, which is now equal to 2. So now the CL value equal to 0.3. From the third term of the code, which is represent the value of P code, so we can get from the value, we can get the value of distance from the leading edge point, where the value is equal to 0.05 times P code value times chord length distance, which is equal to 0.15 L, and the value of A equal to 15% of chord length distance. Okay, from the term number 4, the type of camber line. So because in the 5-digit code, the value that used for Q code is equal to 0. So for this Nakka code 5-digit code, the blade will use normal camber line. Okay, so the last term for this Nakka 5-digit code is value for XX code, where the value is now equal to 1, 2. So from this value, we can determine the profile thickness, where T equal to 0.01 times XX code value 12 times chord length distance. So now T equal to 0.12 L, which is equal to 12% of chord length.
Okay, remember that the T that we discuss here actually refer to the maximum blade thickness, which is referred to the value of T maximum.
So now if we know the value of chord length in terms of chord length distance, let's say L equal to 100 centimeter. So we can determine the value of A, which is equal to 15 centimeter, and the value of T, which is equal to 12 centimeter. Okay, now we look at the example 2.2. So the example or the question asks you to determine the blade profile code for the blade shown in the figure based on A, Nakka 4 digits, B, Nakka 5 digits, where we assume that lift coefficient CL equal to 0.6. So the figure shows the dimension of the blade profile. For question A, Nakka 4 digits, the general code for the Nakka 4 digit is Nakka MPXX. First, we need to determine the value of M code. So M code, we can determine by using this formula: 0.01 times 5 times L equal to B, where L equal to 80, B equal to 4. Thus, M value equal to 4 divided by 0.8 equal to 5. For P code value, the equation will be 0.1 times P times L equal to A. L equal to 80 and A equal to 32. So P value equal to 32 divided by 8. 32 divided by 8 equal to 4. For the final code value, XX, so the formula for XX is 0.01 times XX times L equal to T, where L equal to 80 and T equal to 32. So XX value equal to 32 divided by 0.8, so we obtain XX value equal to 40. So the actual code for Nakka 4 digit for the profile shown in the figures is Nakka 5440. Okay, so for question B, the code for Nakka 5 digits, where we assume that CL value is 0.6. The general Nakka code for 5 digits is Nakka LPQXX. So first, we need to determine the L code value, where L code value can be determined by using this formula: 0.15 times L equal to CL, where CL value equal to 0.6. So L equal to 0.6 divided by 0.15, and the final answer for L equal to 4. Okay, for P code value, so we can determine by using this formula: 0.05 times P times L equal to A. L equal to 80 and A equal to 32. So P value equal to 32 divided by 4, which is equal to 8. And for the Q code value, this value normally depend on the type of camber line used in the blade profile. So because in the blade profile in example 2.2, the type of camber line used is the normal camber line, so the value of Q is equal to 0. Okay, next, the value of XX code, where the equation that can be used is 0.01 times XX code value times L equal to T. L equal to 80 and T equal to 32. So XX for this case equal to 32 divided by 0.8 equal to 40. So the final answer for Nakka 5 digit codes for the profile that shown, the blade profile that shown for example 2.2 is Nakka 48040. There is a website that we call f4tools.com, where through the website we can generate specific blade profile based on your dimension, on your blade dimension or blade parameters. So for example, this is the what I call the toolbox that provide in the website. So you can just type in what I call the value, for example the value of maximum chamber percent, the maximum chamber position percentage, the what I call the blade thickness percentage, and also number of point. Okay, based on your Naka code and so on. So the website will generate the what I call the blade profile for you based on the data that you key in in the text box. Okay, so in case you want to redraw the same blade profile in, for example, in the AutoCAD or in other type of drawing software, the website also give you the data file in terms of X and Y coordinate. You just copy and paste into the drawing software, and the drawing software will generate similar blade profile as shown in the website. Other than that, the website also already provide a database for the different kind of blade profile, standard blade profile, for example Nakka 0006, Nakka 0009, and so on. And by clicking the code, the website will show you the shape of the blade profile. And also you can copy the data file into more X and Y coordinate and paste in your drawing software and so on to redraw the blade profile. Okay, other than that, the website also sometimes give you the data in terms of Reynolds number, lift coefficient, drag coefficient, ratio, and so on. And also the website also provides specific graph, such as the graph that's shown in the slide. So you can try by yourself. Go to the website. Please go to the website and just put whatever you want, whatever data you like, and let's see what kind of blade profile that obtained by the data that you key in the text box from the website. Okay, now to test your understanding about the content of part number 2 for chapter number 2, please answer the question. Determine the blade profile code for the blade shown in the figure based on A. Nakka 4 digits, B. Nakka 5 digits, assume that CL equals 0.6. So you need to answer the question. You have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. So the password was given throughout the video related to this topic. The clue is also given in the link. Okay, good luck. That's all for part number 2. Assalamualaikum.